All right, so welcome. In the last one, let's get into example number 3 for this lesson on graphing rational functions. And so in this one, what we're going to do is work on just identifying the asymptotes again. So now that we've talked about the vertical, the horizontal, and the oblique asymptotes, we're going to go back and circle back to talking about how to identify symmetry as well as the X and Y intercepts. Now, I'll have a little fun with the graphing. I do have a link here that you can follow, so therefore I plugged all of these into Desmos, so you can go ahead and check your work. But kind of based on the information, you should have a rough idea what the graph looks like. Obviously, you could always create a table, but I don't really want this lesson to be about just graphing. It's really about identifying the important parts, because most of the time, if you ever need to graph something like this, we'll just want to use a calculator. But I will kind of, at least these important points will give us usually enough information so we can identify what the graph would look like, or we could just use our table values to fill them in. So you can see we're just going to do 3, 6, 9, 12, 15 examples. So we got quite a bit here. All right, so let's go on to this and kind of get started here. And we're just going to kind of work through each and every one. Now, one of the things that I wanted to remind you of to kind of shorten things up, remember that when we're identifying, sorry about that. Remember when we are identifying the X and the Y intercepts, for the X-intercept, Y is equal to 0. And for the Y-intercept, X is going to be equal to 0. So let's have X. I'll switch it up. So for the X-intercept, we're just going to do Y is equal to 0. Now again, I'm using function notation here, but we could easily just replace all of these output values with a Y. Okay, so I'm not going to do that for each and every one. We're just going to use that. So therefore, if I set that equal to Y, I have 0 equals 2 over X squared minus 1. I'll add the 1 to the other side, so I get 1 equals X squared. 2 over X squared. Actually, this one I'll show my operations. How about that? Then to get the X squared off the denominator, we're going to multiply by X squared on both sides, and therefore I'm left with an X squared equals 2. Now, to solve for X, I need to introduce the square root. And just remember, when you're introducing the square root, you have to include X equals plus or minus the square root of 2. So my X-intercepts are going to cross that square root of positive 2 and negative 2, which is not going to be very easy to graph. Hence, really why I don't want to focus on graphing, but more importantly, just identifying the information. For the Y-intercepts, X is going to equal 0. So therefore, we have, let's just say Y equals 2 over 0 squared minus 1. And immediately we see there's an issue here, because we can't plug in 0 into the denominator because that's going to be undefined. So we'll say there's no Y-intercepts. So right now, the only thing we know about this graph is that it's not going to cross the it does not cross the y-axis, but it does cross the x-intercept at 2 values. Let's go ahead and take a look at the asymptotes. So to identify the vertical asymptote, you can see that that is, so remember, the vertical asymptote is basically going to be the values that make the denominator equal to 0. So that's x squared is equal to 0. Well, obviously you can see that if you take the square root of both sides, you can see there's a vertical asymptote at x equals 0. For the horizontal asymptote, we need to use the horizontal asymptote test. So we're basically going to be comparing the degree in the numerator with the degree in the denominator. And since there's no variable here, we can put a x to the 0. So therefore, we see that the degree in the denominator is larger than the degree in the numerator. So therefore, the horizontal asymptote is going to be at y is equal to 0. Horizontal asymptote. Oh, y is equal to 0. Yes, that is correct. But what you can see here is the graph is being shifted down 1. I was like looking at it, I'm like, that's not what I had. So since this graph, though, you can see this has a -1. This is because this is actually not in, and I should have mentioned that at the beginning. This is not in a rational function form. It's not one polynomial over another polynomial, and it's not a reciprocal function either. Because the reciprocal function has that variable linear. So what we could do, if we wanted to do this, we could get this to be a common denominator. So x squared over x squared, and therefore this function could be really written as y equals a negative x squared over x squared. So that is another way to write it. So now it's in a rational function. And I should have mentioned that at the beginning. I apologize. But that comes up. The reason why that's important is you're doing the rational zero test. That's correct, but it has to be as a rational function, right? So rational function. So we have the x squared over the x squared. So therefore, you can see that they're the same. So it's at a -1. So y is equal to -1. So when you do the rational function test here, you can see that the numerator and denominator have the same degree, but it's at -1. But it's -1 over 1. So because that's the ratio of the coefficients. So that's why the horizontal asymptote is at -1. And let's see here. I think that was symmetry. So remember, to test symmetry, we're basically going to evaluate for f of -x. So to test symmetry, I'm just going to plug in f of -x. And remember, if we get the exact same function out, then I have a function that is symmetrical about the y-axis, and it is an even function. And if I have the exact opposite of the function, therefore it's symmetrical about the origin, and the function is called an odd function. Well, here, when we plug in -x, you can see we get the exact same function out. And if I was to do it up here in this equation, I'd still get the exact same. So therefore this graph is symmetrical about the y-axis. So if I was just going to do a rough little sketch here, I know I have a horizontal asymptote. Let's do a different color. Let's use red. I would have a horizontal asymptote at -1, a vertical asymptote at x equals 1. Let's see, I have an x-intercept at square root of 2. That's going to be like 1 point something. So therefore, let's just put that there. This would be negative square root of 2. This would be positive square root of 2. That's obviously at -1. So the graph is approaching this asymptote and approaching this asymptote, but it has to cross at these asymptotes. So you could do a table of values, but since I know the graph has to approach these two asymptotes, I'm just going to do something that's going to look something like that. And it's not perfect, and it has to be symmetrical, right, as well. So there's a rough understanding for these. So this one I worked kind of everything through. For the rest of the videos, to make this video not last so long, I'm going to kind of work on everything a little bit quicker, or at least not explain like each and every step. So the x-intercept in this case, y is equal to 0. Now again, this is an important one. I'll do this one more time because this is in a rational function form. So I will show my step here, but I'm not going to show this for the rest of them. Remember, one thing we investigated earlier in this lesson is when you have a function, a rational function set equal to 0, to get rid of the denominator here, you're always going to be having to multiply by that denominator, right? And so what happens, since it's equal to 0, we're always going to get the numerator equal to 0. So for the rest of the time, anytime we have a rational function, we're trying to find the x-intercept, I'm just going to set the numerator equal to 0 and solve. And that's why, because I'm not going to have to go through this step. It's redundant. It happens every single time, unless it's in a reciprocal function. That's why I did my inverse operations. But if you rewrote it as this way, you still would have got the same answer. So therefore, I get x is equal to 0 in this case. For my y-intercept, I'm going to put x equal to 0, so I'll have y is equal to 4 times 0 over 0 minus 2. So let's see, that's going to be 0, so it doesn't matter what's in the denominator, y is equal to 0. So therefore, this graph has a x and y intercept at the origin, right, at 0, 0, comma 0. Let's go ahead and find the vertical asymptote. So the vertical asymptote is the values that make the denominator equal to 0. So that's going to be at, so you set your denominator equal to 0. So therefore, I can say x is going to equal 2. For my horizontal asymptote, I need to compare the degrees. Notice that these both have a degree of 1. So it's going to be the ratio of the coefficients, kind of like what we did here. This one was a -1 over 1. This one's going to be a 4 over 1. And again, remember, it's y equals that ratio. So y equals 4 over 1, which is just equal to 4. We don't need to write the 1 in there. Now let's go ahead and test our symmetry. So we'll do g of -x is equal to 4 times -x divided by -x minus 2. And when doing that, we get a -4x over a -x plus 2. And that would go ahead and those turn to a positive, so we can see that this is not going to be the exact opposite. So we just say there is no symmetry. Okay, so let's go and plot the information that we do have. So we have a vertical asymptote at 2. So I'm going to go over to 2. Horizontal asymptote at 4. And we have a X and Y intercept at 0. Right? So to go ahead and take a look here, I want to go and plot that out. So this one looks like, since it has that vertical stretch and that horizontal compression, this graph. Now again, this might not be enough. The only thing you do know, and obviously I'm just using the graph, so like this might not be enough. You could look at this and say that, oh, well, we could use long division to put this in the reciprocal form, which is correct. That's exactly what you'd want to do in this case. Or you could also just create a table of values to kind of see the direction that this graph is going. But understanding that the graph has to cross here and approach the two asymptotes, and then also that it's going to have that reciprocal relationship, then you know that the graph would look something like that. All right, on to C. So next one is the X-Intercept. Again, now I'm just going to set my numerator equal to 0. Divide by 2, so I can just say x is equal to 0. For my Y-intercept, I'm just going to plug this stuff in. So this becomes, 0 over, let's say, -4. So obviously it's just going to be y is equal to 0. So I'm kind of working my way a little bit quicker here. Let's go ahead and get into the vertical asymptote. That's going to be x squared minus 4 is equal to 0. You can use the difference of two squares or just solve this to give x equals plus or minus 2. And the horizontal asymptote, you can see again that we have a same power, same degree. So it's going to be the ratio of the coefficients, which in this one is going to be y equals a -2 over 1, which is just a -2. And the next one we'll do is symmetry. So we'll do g of -x. So we'll do -2 times -x squared all over -x squared minus 4. And you can see when we do that, that is going to give us the exact same function because everything is going to be squared. So therefore, this function is even. I didn't write that in this one, did I? I said no symmetry here. Symmetry, this one is going to be even. Or symmetrical about the y-axis. It's really, the same thing. All right, so let's go ahead and plot the information that we have here. So we have X and Y our X-intercepts at +2 and -2. And that kind of gives it away too as far as our symmetry. Like we have X-intercepts like on either side that they're equal. Like that usually kind of means something there. Oh, those are my vertical asymptotes. Sorry about that, not my intercepts. Those are my vertical asymptotes. My horizontal asymptote is at -2. And I have an X and Y intercept at 0, 0. Okay, now typically if I was to graph this and I didn't have graphing technology, what I would do is I would choose 2 points to the left and 2 points to the right of either asymptote. And sometimes you might need 3 points. And I would just plug those numbers in for X. So for instance, I'd probably pick like -3 and -4, find their Y values, and then graph them. Now the nice thing about having symmetry is if you do -3 and -4, you don't have to do +3 and +4. Those values are going to be exactly the same. So I would just pick 2 points to the right of this asymptote, 2 points to the left of that asymptote, identify the shape of the graph there, and then just reflect it. That's the kind of nice thing about having symmetry in this case. Oh, actually I didn't graph this, so I messed that one up. So I'm going to put this up real quick, and then I'll come back. Okay, so now go ahead and take a look at that. Let's see here. This is going to be, that's not a horizontal asymptote at -2. Oh, wrong one. Shoot. There we go. Okay. So now we're going to take a look at this graph here. Let's go ahead and use blue. So again, by looking at this, what we see is this graph is going to be approaching these two asymptotes here in this formation. And then we're going to have a little quadratic here. But again, remember, it's not going to be further expanding, but it's going to be approaching the asymptotes. All right, on to the next one. Now we can see we just have a polynomial in the denominator, but one is a polynomial, so just no variables here in the numerator. So to find the x-intercept, that's just going to be y is equal to 0. So basically going to set the numerator equal to 0. And you can see that that doesn't make sense. 1 does not equal 0. So therefore, there is no x-intercept. For the y-intercept, we're basically going to put in a 0 in for all the x's. So anytime you put a 0 in for the x's, you're going to have a 0. So it's basically just going to be 1 over 2. Let's go ahead and find the vertical asymptote is basically the values that make the denominator equal to 0. So it looks like we're probably going to have to do some factoring. Hopefully not the quadratic formula, but this is factorable. I can see what two numbers multiply to give me 2, add to give me a positive 3. That's going to be an x plus 2 times an x plus 1. So therefore, I can set these both equal to 0 and solve. So I get x equals a negative 2 and x equals negative 1. To find the horizontal asymptote, I notice that, again, my degree in the denominator is larger than the degree in my numerator. So I have y equals 0. And then if I want to go ahead and test my symmetry, I can already see that this is not going to be symmetrical, because if I plug this in, negative x, that's going to be a positive, that's going to be the same, and that's going to be an opposite. So whenever you're testing symmetry and you see that the power of the degrees is not always consistent, now again, this is just one way, because there's multiple ways that it can still be, no symmetry. But to save myself time, since I see this degree here is even and this degree here is odd, I know that I'm not going to have symmetry, because you're going to have symmetry about the y-axis when all of your variables are only raised to an even power. So if all of your variables are not going to be raised to an even power, then you're not going to have symmetry about the y-axis. So since here I have even and odd, it's not going to work. And then also, it's never going to be odd if your variable is raised to an even power. So at least when we're dealing about this polynomial sense, there's different when we start talking about different functions. But when we're just looking at polynomials, if you have a variable that's raised to an even power, you're not going to have odd symmetry. So therefore, this has none. And again, if you want to plug it in, like plug in negative x, that's fine. You would get 1 over x squared minus 3x plus 2. And you see that that is nor the original function, nor is it the exact opposite of the function. All right, so let's go ahead and graph what we have here. So we have no x-intercept. We have a y-intercept at 1/2. So let's just say 1/2 is right there. We have a x-intercept. Y-intercept is not a thing. We have a horizontal asymptote. I'm going to have to use purple. We have a horizontal asymptote at y is equal to 0. We have a x-intercept at 1/2. So let's put a 1 right there. There's no x-intercept, but we do have vertical asymptotes at x equals negative 2 and negative 1. Let's move that to the side. So this one would not be very much fun here to identify the points, what's happening inside those two asymptotes, because basically you'd have to go ahead and use fractions. But you can do it. Like, it's not anything that's going to be crazy. You can definitely go ahead and do it. And what you'll see is you'll get some negative numbers each and every time you do that. So by looking at this graph, again, what I would do is just create a table to the left, to the right, to the right. And basically you're going to see a graph that's going to look something like this. Oops. Remember, it's approaching those asymptotes. And then here the graph is looks something like that. It's just going to be a hyperbola. I think that went down to like -4 was that point, somewhere right around there. And then it's going just showing down. So it's like a parabola, just again facing down, as these two approach both the vertical asymptotes as well as the horizontal asymptote. All right, next one, h of x. So in this one, the x-intercept we're setting the numerator equal to 0. So we get x is equal to 1. For the y-intercept, we have y is equal to, let's just do 0 minus 1 here is negative 1. That's 0 over 2. Now let's go and do the vertical asymptote. Is again setting my denominator equal to 0. So x squared minus 3x plus 2 equals 0. In this case, again, we can factor it, but now instead of my two terms adding to give me a positive 3, they're adding to give me a negative 3. So that's going to be an x minus 2 times x minus 1. So therefore, x is equal to positive 2, x equals positive 1. And my horizontal asymptote is also, again, the degree in my denominator is larger than the degree in my numerator. So it's still going to have a horizontal asymptote at y equals 0. Again, I'm not going to have any symmetry because I noticed that they don't have the same powers. So symmetry is going to be none. So let's go ahead and graph what we have here. So in this case, we have a horizontal asymptote at y equals 0. We have a vertical asymptote at 1. Not very straight. A vertical asymptote at 2. So that would be 1. This will be at 2. All right, let's see. We have an X-Intercept. That's not right. What happened here? X-Intercept at 1. Y is going to be equal to 0. X minus 1. Y-intercept at negative 1/2. So we have a negative 1/2. I'm going to look at my graph, what I did here. No, this one. Yeah, it's not crossing. The x-intercept is when y is equal to 0. Why is that not giving it to me? X is equal to 1. Well, that's interesting. I don't think I've, oh, I'm an idiot. I wasn't thinking about this. Duh, we got to remember our holes. I was like, what happened here? So we come up with a problem, and again, I kind of forgot I had this problem here of what I was doing. So we don't have a vertical asymptote at negative 1. And the reason being is if we were to simplify this, like be a little strategic here, if I factor this into x minus 1 over x minus 1 times x minus 2, what we notice is the x minus 1s divide out. So I noticed my problem, and you should always look into factoring and seeing if you could divide something out first and identify the holes, right? Because that's going to create a hole. So the issue comes into, it didn't make sense for me to have an x-intercept at 1 as well as a vertical asymptote at 1. So you're going to have that issue. If you still working, you're going to have that issue, and you're going to notice there's a mistake there. So what happens is we don't have an asymptote here. We have a hole. Okay, so the graph is going to cross. Don't want that. Here's going to be at. Okay, so the graph still crosses at negative 1/2, but now there's going to be a hole here. And now it needs to approach here, this horizontal asymptote. So I'm going to go from there. But now what I'm going to do is I'm just going to put a nice little hole right there. And then obviously you can see that when I simplify this, when that is simplified, that gives me the equation h of x is equal to 1 over x minus 2. Well, that's just the reciprocal function, right? That's just a reciprocal function shifted 2 units to the right. But again, remember there's that hole at 1. Okay, so, and again, you can determine that hole at 1, and you can see that it's going to, when we plug that in, you can see it's going to be at negative 1. So the hole is at 1 comma negative 1. And again, I got that just by plugging a 1 into x. So if you plug a 1 into x, you can see you get negative 1, and that's how I got that. Okay, so be careful. And that's, kind of note to me to remember, even though I worked on all these functions, I kind of forgot the work I did because it was actually a couple weeks ago. So in this case, I can see that this one's factorable as well. I can factor this into x plus 1 times x plus 1 all over x plus 1, right? So now I can see that my x plus 1s divide out. So what that's going to do is that's going to leave me just with x plus 1 with a hole at x is equal to -1. Or we could write that as a coordinate point. So by plugging in a -1, I can see that I'm going to get at -1, 0. Okay? So, so therefore, if I notice, like here's my equation, I'm not going to have a vertical asymptote. I'm not going to have any horizontal asymptotes. My equation is just a linear line, x plus 1. So let's go ahead and, so vertical asymptotes, you can see as this gets simplified, there is no vertical asymptotes because it's just a hole at my discontinuity. Horizontal asymptotes, there is no horizontal asymptotes. When this gets simplified, you can see it's just a line. There is no horizontal asymptote, so that's none. Symmetry, you can see this is a linear line, so there's going to be no symmetry. And then I did forget to do the X and Y intercepts. So the X-intercept is going to be at -1, right? But we notice that x cannot equal -1, right? So therefore, because that's where there's a hole. Excuse me. Yeah, because there's a hole at -1. So the X-intercept is going to be none. And my Y-intercept is when x is equal to 0, which is going to be 1. So that would be y is equal to 1. So let's go ahead and graph this. Okay, so if I was using my point slope form, I'd be going up to 1. And then remember, you go like up 1, over 1, and you graph a line. But remember, our hole here is at -1, 0. So my graph is just going to look like that. It's a nice little line, no asymptotes, but just has a hole at -1. All right, on to the last 6. So next one, you could definitely go ahead and rewrite this as a rational expression if you wanted to. I'm just identifying the information, so I'm not going to be concerned as much with graphing it. So I'm just going to go ahead and find the x and y intercepts rather quickly. X-intercept is numerator equal to 0. X is equal to -4/3. The y-intercept is going to be 0, 0, so that's y is equal to a negative, or 4 over -1, so that's just going to be y equals -4. For my vertical asymptote, that is my denominator set equal to 0, so that's going to be x is equal to 1/2. My horizontal asymptote is, again, the horizontal asymptote test, which you can see here is just going to be, since the degrees are the same, it's going to be the ratio of my coefficients, which is y equals 3/2. Symmetry. Now for polynomials, when you only have odd symmetry, you don't want to just assume it's odd, because when you have these variables, when you have constants, it actually affects that symmetry. So I'm not even going to plug it in. I know that when I'm having odd powers and I also have constant, it's going to be, there's not going to be any symmetry at all. It's not odd. It's definitely not even, because these powers seem to be even, but it's not going to be odd, because if you plug that in, again, if you plug in -x, you would get a -3x plus 4, right? Which is not the opposite of that, not the opposite of those terms. So it doesn't work. So therefore, my symmetry is none. Whoa. All right, so now let's go ahead and sketch what we believe this to work out as. So we have a x-intercept at -4/3. So that's like -1 1/3. We have a y-intercept at -4, I'm sorry. 1, 2, 3, 4. We have a x-intercept at +1/2. So I'll put like 1 here, so therefore +1/2. And we have a y-intercept at 3/2, so that's like 1 1/2. Okay, so again, just kind of understanding that this is going to produce, if we were to do long division, this is going to produce a reciprocal function. We can just kind of know that we're going to have that hyperbola shape with both of our graphs approaching the x and the y axes. All right, on to the next one. So this one is 4 minus x squared divided by x squared plus 5. It might be helpful to go ahead and rewrite this as a -x squared plus 4 all over a x squared plus 5. All right, and it looks like it could be a potential, reciprocal function again. So let's just go and identify our information now and kind of see. If I'm going to find my x-intercept, again, that's just going to be my numerator equal to 0. So 0 is equal to a negative x squared plus 4. So if I subtract a 4, that becomes a negative 4, right? So I have a negative 4 equals negative x squared. But then I divide by negative 1, and I get a positive x squared. So therefore, I can see that this is going to give me two real solutions, x equals plus or minus 2. For my y-intercept, I'm just going to plug 0 in for x. So therefore, that goes to 0, and that's a 0. So I'm going to have y is equal to 4/5. And if you've already kind of noticed, the y-intercept, I forgot to mention this earlier, the y-intercept is really just the constant over the other constant, right? Because all your x's always go to 0. So for the x-intercept, you set the numerator equal to 0 and solve. For the y-intercept, it's just constant over constant, constant over constant. Y equals, constant over constant. All right, let's go and look at our asymptotes. So our vertical asymptote is the values that make the denominator equal to 0. Well, what we notice here is when we solve in this case, we have negative square root of 5, or negative 5. Well, I can't take the square root of a negative number, so there is no vertical asymptotes. For my horizontal asymptotes, I'm going to use the vertical or the leading coefficient test, which you can see here is negative. Since they have the same degrees, it's going to be negative 1 over 1. So that would just be y is equal to negative 1. All right, so we have two x-intercepts. So we have positive 2 and negative 2. Symmetry, I forgot to test symmetry. You can see here it's even, and then constant, constant. So this would work. This would be symmetrical. Forgot to mention that, so let's talk about that. So the symmetry here is even. All right, and you can also notice that the x-intercepts plus or minus, that helps it, right? The y-intercept is at 4/5, so that's going to be 1 1/5, so like be up there. And we have a horizontal asymptote at negative 1. Okay, so it kind of looks like it's going to be a nice little bell curve here. We'll just go ahead and double check. Make sure. Again, you can check with decimals, and yep, that's exactly right. So it's not the reciprocal function, so be careful. Just because something has the 2 degrees, even though you can divide them into each other using long division, doesn't mean it's going to give you that reciprocal function. That's only for the linear over the linear. Next example here is, 12x to the third, 3x squared plus 1. All right, let's do it. So x-intercept. X-intercept, numerator equals 0. 12x cubed equals 0. X will be equal to 0. For my y-intercept, I have constant over constant, but again, you notice that my numerator will be 0, so that's just going to be y is equal to 0. Vertical asymptote is the values that make the denominator equal to 0, so 3x squared plus 1 is equal to 0. And again, you're going to, whatever, it doesn't matter, you can't take the square root of it, but again, it's going to be negative, right? So there are no vertical asymptotes. As far as horizontal asymptotes, you can see here now that my numerator is larger than the degree in my denominator. So therefore, there are no horizontal asymptotes. But now I need to check for my slant asymptotes. All right, so I'm going to have 3x squared plus 1 divides into 12x cubed. So 3x squared divides into 12x cubed, 4x times. 4x times 3x cubed is going to be a 12x cubed. 4x times 1 is a positive 4x. When I subtract my terms, this could be a possible 0x there as a placeholder, and you get a negative 4x. But it doesn't really matter what your remainder is, because even though you can write that as the quotient, right, you take the remainder over the quotient, that's going to eventually approach 0. It approaches that asymptote before the 0. So all we're concerned about here is the quotient. So my slant asymptote is at y is equal to 4x. Okay, so that's going to be a linear line here at 4x, pretty steep. All right, so let's go and sketch here what we have. So we have a pretty vertical 1, 2, 3, 4 over 1. 1, 2, 3, 4. Do 1. So we have a pretty vertical slant asymptote. We don't have any vertical asymptotes. We don't have any horizontal asymptotes. And X-intercept is at 0, 0. Y-intercept is at 0, 0. What the heck did I do with this one? Yeah, oh, that's really weird. I don't think I remember. Actually, I didn't sketch this graph, so this is kind of weird. So again, the important thing here, when looking at this graph, is like, well, it can't cross like the asymptotes. Well, yes, actually, it can. So I actually want to look at this graph a little bit more closely. Yeah, so that's cool. That's cool, man. I didn't even look at this graph before. So this graph kind of goes like this, and then it crosses, and then it goes like that. So a lot of people get confused with asymptotes because they say, oh, it can't cross the asymptotes. Well, no, it can't cross the discontinuous asymptote, which is the vertical asymptote, right? Because vertical asymptotes are when the function is undefined. Horizontal asymptotes is not when the function is undefined. That's just where the graph is approaching horizontally, and that's the same thing for the oblique or the slant asymptotes. It just means where the graph is approaching, moving left to right, right? It's not where it's undefined. So the function is never, ever going to cross a vertical asymptote. It's only approaching vertical asymptotes. However, it is possible for it to cross horizontal and slant asymptotes. It doesn't occur often, but it can occur. There's nothing wrong with that. It's still defined for all of those values. So horizontal and oblique asymptotes are not discontinuities. That's why they can cross. The main important thing is that they are approaching those functions. Okay. All right, on to the last three. And yeah, I was kind of confused because, well, I didn't graph these. I worked through all the information, but I didn't graph them. So I was I don't think I've actually worked on that function before in all my examples. So kind of cool. All right, let's do another one. So this one, g of x here, X-intercept is going to be when the numerator is equal to 0. So x squared plus 2 is equal to 0. Again, if we try to solve this, we're going to be taking the square root of a negative number. So therefore, there are no x-intercepts. For the y-intercept, if you put a 0 over here and a 0 over here, you can see that, again, you can't have a 0 in the denominator. So there are none. Vertical asymptotes, that's going to be values that make the denominator equal to 0, which is 0. The horizontal asymptotes you can see here is, again, the degree in the denominator is smaller than the degree in the numerator, so there are none. Now what we're going to need to do in this case is, again, check for oblique asymptotes or the slant asymptotes. So we're going to do a little division, so x divides into x squared plus 2. So x goes into x squared, x times x is x squared. Subtract, you have 2. X is not going to 2, so that is your remainder. But again, we're not concerned about our remainder. Our slant asymptote is just going to be the quotient without the remainder, which is y equals x. I totally forgot to check for symmetry. And that's kind of important. Now, this one will be none. Although it does look like it has odd symmetry. Actually, I made a mistake. Let's actually check the symmetry. Because that was for polynomials when you have an odd and a negative. But in this case, if I plug in f of negative x, I have a 12 negative x cubed divided by 3 negative x squared plus 1. Okay, so when I simplify that, I get a negative 12 x cubed. That turns positive, and therefore I have a 3x squared plus 1, which I can take that negative now and put it in front. So therefore, I can rewrite this as a negative 12x cubed positive 3x squared plus 1. So I did misspeak, and I do apologize for that. I did say, well, whenever you see that there's going to be a positive and a negative, it's not going to be neither or odd. And that is true when you're dealing with polynomials. But since you have a polynomial in the numerator and the denominator, then that's not going to be true. That's not going to be the case. So you always have to. That's why it's important to test it. And I got a little lazy and decided not to test it. Well, actually, I just forgot to test for symmetry, so I didn't even look at it. So that's why. But you can see here, this has symmetry about the origin. So therefore, it is odd. So therefore, the symmetry is odd. I just want to make sure we cover that. Okay. All right, so in this one is, now let's go and test the symmetry here. Oh, no, okay, cool. So let's work this one out. So I have g of negative x equals negative x squared plus 2 all over negative x. And here, again, I'm going to have a x squared plus 2 over negative x, and I can factor that negative out in front. So you can see that it's the exact opposite again. So therefore, this one is going to have odd symmetry. Now, I am running out of space, so that is not very good. All right, so let's try to maybe fit something in here real quick. So we don't have a y-intercept. Our x-intercept doesn't have an x-intercept, doesn't have a y-intercept, has a vertical asymptote at x equals 0. So let's use brown. Our vertical asymptote, I'm sorry, equals 0. And no horizontal asymptote, but we do have a slant asymptote at y equals x, which is the function there. And I would assume it's going to be kind of like two curves right here, but let's just go ahead and double check what I have here, and that's that one, x squared plus x. Yep. So that graph just kind of looks like approaching your two asymptotes there and approaching your two asymptotes there. Okay, so you can see it definitely doesn't cross x or the y-axis. All right, on to the next one. Now this one might look factorable, but it's not. If I was to factor this out, I get x. Well, actually, that's non-factorable, so that's not going to work. So that's kind of important, though, because when I want to find my x-intercept, I'm setting my numerator equal to 0, right? So x squared plus 2x plus 3 is equal to 0. And then I'm like, oh, crap, why don't I put this down below? I'm like running out of space. So x squared plus 2x plus 3 equals 0. So what I'm going to want to do in this case is I'm actually going to test the discriminant. So remember the discriminant is b squared minus 4 times a times c. I want to see, do I need to use, am I going to use irrational, or is there going to be complex numbers, so therefore there'd be no real x-intercept? So what I'm going to do is I'm going to do 2 squared, which is 4, minus 4 times 1 times 3. And I can see that's going to give me a negative number. So therefore, there is no x-intercepts. For the y-intercepts, I'm going to set everything equals 0. So it's basically constant over constant, which is y equals negative 3. All right, vertical asymptote is the values that make the denominator equal to 0. So that's x equals 1. Horizontal asymptotes is, again, you can see that degree in the denominator is smaller than degree in the numerator, so therefore that's none. So now we need to check the slant asymptote. Where's that other one I had? Yeah. Just looking back at my stuff. Okay. So that means now we got to do some long division. So x minus 1 divides into x squared plus 2x plus 3. So x goes into x squared, x times x is x squared. X times negative 1 is a negative x. Group and subtract. X squared goes into x squared, x, or 0 times. So 2x minus a negative, that's going to be a 3x. And then 3 minus 0 is just going to be a positive 3. X goes into 3x plus 3 times. 3 times x is 3x, and 3 times 1 is negative 3. It doesn't matter here again that my remainder is 6 because again we're only concerned here. So the slant asymptote is y equals x plus 3. Let's go ahead and check our symmetry because we run out of work. All right, and again for symmetry, it's not gonna, doesn't have any symmetry, but let's just go and do it anyways, just so you guys can see. So k of negative x is going to be if I plug in a negative x squared, I'm going to have an x squared. That would be a minus 2x plus 3 all over a negative x minus 1. And you can see that's not the original function. And if I factor out a negative, it won't give me the exact opposite. If I factored out a negative, it went like, see here, I factor out the negative and I got the original function back. If I factor out a negative, I'm still not going to get the original function. So therefore, there is not any symmetry. Actually, what I'll do is I'll just write none over here. So now let's go ahead and see what this graph looks like. Let's use blue. Fix that. All right, or green, I guess. So we have a vertical asymptote at 1. Slant asymptote at x equals 3, or x plus 3. So at 3 is going to be a y-intercept. There's something going there. Let's see, what else we got? There are no x-intercepts, and there's a y-intercept at -3. So again, what this tells me is it looks like this graph is going to be doing another one of those hyperbolas across. Let's kind of see here. And that is correct. So unfortunately, I'm going to be kind of graphing on top of something I've already graphed here. You can see the graph is going to go out like that, and then this would probably shoot out like that. So let's maybe continue the green here a little bit, kind of going through my work. But again, you can just kind of see that since it's not going to be crossing the x or y axes here, it's going to take some short. And again, if you're not sure about this, like obviously I have the link available for you on Desmos, but you can just create a table of values. All right, so last but not least, guys, we're almost there. So in this final example here, and I'm like losing my space here. So the x-intercept, I'm not going to want to factor this, is going to be numerator set equal to 0, so I'm going to factor out a negative, and that will leave me with a x squared minus 4x minus 3 equals 0. Which again, I know that's not going to be factorable, so I'm going to test my discriminant here. So therefore, that's going to be a 16 minus 4 times -1 times my c. Oh, crap. No. Yeah, it's a. So b squared minus a times 3. And you can see here, I have -4 times -1 is +4. +4 times 3 is going to be 12. 16 minus 12 is going to be 4. So I'm going to have the square root of 4, which is 2. So that means that is factorable. What the heck did I do wrong here? That's a negative. That turns into a negative. -3 minus 1. Okay, now it's crap. Now I'm making my mistake in the last video. All right, let's slow it down. X equals opposite of b plus or minus square root of b squared minus 4 times a times c all over 2 times a. So it's a -4 plus or minus. Let's see, that's going to be 16, and that's a +4 times 3 is 12, so that's going to be, that's right, I'm going to add those, so that's going to be 16 plus 12, which is 28. Okay, and I can factor that into going to be a 4 times 2, so that's going to be 2 radical 7. Okay, so I'm going to erase all of this. And since I've been kind of going over it, so again, I tried to set it equal to 0. It didn't really make sense to factor out the negative because it's non-factorable. So I'm just going to set this here as negative x squared plus 4x plus 3 equals 0. And I'm just going to say by the quadratic formula, so by the quadratic formula, I am going to get -4, and that's going to be all divided by -2. So let's see here, that's going to be, so x is equal to -4 plus or minus 2 square root of 7 divided by a 2 times a, so that's a -2. So by quadratic formula, I am going to have x is equal to a 2 plus or minus square root of 7, because those divide into giving me a +2, and those are going to divide me to equal to 1. Okay. Hopefully you got a good, nice little refresh on quadratic formula. For the y-intercept, Again, guys, it's just going to be constant over constant here. But you can see here, like, there's no constant in the denominator. So then what are we doing? Well, again, we're going to look at the power in the denominator. Oh, sorry, y-intercept. If you plug 0 in for all of the x's, you're going to have 0 in the denominator. So that's going to be none. Vertical asymptote. Vertical asymptote is the values that make the denominator equal to 0. So I'm going to factor out an x. By factoring out an x, I am left with a 2x squared minus x minus 3. And now basically I want to see what values make that equal to 0. So I want to see if this is factorable. And let's see, I can do 3 and 2. Yeah, so that should work, hopefully. Let's see, I'm going to want to multiply this to give me a positive 2. So this would be, let's make that a negative 1 and that a positive 3. And let's double check. 2x times x is 2x squared. 3 times negative 1 is negative 3. That gives you a positive 3x. That gives you a negative 2x. No. So I need to change my signs to make that be a negative and that be a positive. Okay, that's going to give me a negative x. So therefore, my vertical asymptotes are x equals 0, x equals 3/2, and x equals negative 1. Horizontal asymptote, since the degree in my denominator is greater than the degree in my numerator, I am going to have, since the degree in the numerator is equal to the degree in the denominator, I am going to have a horizontal asymptote at y is equal to 0. And then for symmetry, that is neither and that is neither. So then obviously for them both together is not going to produce any symmetry. So therefore there is none. And again, you can just check your work, check my work here. So let's go and see what we got here. So we have these crazy X-intercepts. Now the square root of 2 is 2.6457513, at least approximated. So therefore, if I was going to add a 2 and subtract a 2, I'm going to be dealing with like a 1.6 and then a 4.6. So 2 minus square root of, so it'd be, I'm sorry, 2 minus that would be like a 0.6. Okay, and then, oh, no, it's 2 minus 0.6. That'd be a negative 0.6. And then 2 plus, oh, come on. 2 plus 2.6. And again, you can just approximate this, right? I know that the square root of 4 is 2, the square root of 9 is 3. So it's between 2 and 3, right? So therefore, just pick 2.5, like for approximations. So if you have 2 plus 2.5, that's 4.5. Right? It's like 4.6 is the approximation. If you did 2 minus 2.5, that's negative 0.5. And again, the approximation is like 0.6. So we're not too far off. So that's going to be 5 over there. All right, and then we have quite a bit of vertical asymptotes here. I'm going to go back to red. So we have a vertical asymptote at 0. We have a vertical asymptote at 3/2, which is basically a 1.5. And we have a vertical asymptote at x equals negative 1. And a horizontal asymptote at y equals 0. Now, I have no idea what this graph looks like. I'm kind of interested here. Whew, that is a lot going on. See if I can. All right, there's definitely no symmetry going on with this one. So this graph, or again, remember guys, if you have asymptotes, that means it's going to be approaching the asymptotes, right? So we have a hyperbola, and you'd probably need to do a pretty crazy table to really make sure you had everything here. This is going to be crossing like a little S curve here. Here we have a parabola, and then it approaches over here. So a really cool graph. And again, you can see that there's no symmetry. You obviously got to test it out. But again, guys, I'm using technology to graph this because I'm not really too concerned about my students being able to graph this. It kind of takes too long to really like plug in the values. And it's helpful, I mean, but I think most students know how to graph a function using a table. So my main keys is, can you find the X and the Y intercepts, rather quickly? Can you identify the asymptotes? Really important. And then also just remembering, how to identify symmetry. And I think that is what is most important about graphing rational functions. The actual graphing portion of it. As long as you know how to graph other functions, I use just technology for my students to be able to do this. So because of that, and if you do need to, then you can just apply the skills. But I don't think it's something that we need to overtly practice over and over and over again to be able to do. But either way, hopefully this is helpful. And now we'll get on to the last section in this course, which is solving rational expressions.